Okay, welcome everyone to the latest episode of Scrubbing the Skies, the webinar series of the Institute for Responsible Carbon Removal at American University. As always, I'm the host, Will Burns. The Institute focuses on helping to develop the contours of what constitutes responsible carbon removal and hopefully helping to operationalize that vision in the medium to long term. But today, we're doing something a little different. Instead of focusing on a topic associated with carbon removal, we're looking at an emerging and in some ways allied climate intervention, which is atmospheric methane removal. In October of last year, the U.S. National Academies of Sciences released a report that focused on both the rationale for a research agenda for atmospheric methane removal, as well as recommendations on how that would ensue. And so today we thought we would dive into this issue a bit more. And we have a number of participants, some of which were directly associated with this report, and some of whom are experts in methane removal that have helped inform the ideas that have developed in this report. And so at the outset, I want to introduce our participants today. First is Gabby Dreyfus, who is Chief Scientist for the Institute for Governance and Sustainable Development, as well as an adjunct lecturer at Georgetown University. Gabby served as the chair of the NASEM study committee for the report that I've just referenced. Second of all, Rob Jackson, who is Douglas Professorial Professor of Energy and Environment at Stanford University, chair of the Global Carbon Project, and a member of the NASEM Study Committee. Third is Hannah Horowitz, who is an assistant professor in civil and environmental engineering at the University of Illinois, Urbana-Champaign. Fourth, Holly Buck, Associate Professor of Environment and Sustainability at the University of Buffalo, as well as a NASEM study committee member. And finally, David Mann, who is co-founder and head of strategy for Spark Climate Solutions. So welcome to all of you. And here's how we'll proceed logistically. First of all, we'll have a fairly extensive initial intervention, a series of presentations that are a little longer than what we usually do, because I am going to presume that for many of our audience members, this may be a new topic. After that, I'll proceed with a couple of questions to seed the conversation, and then we will immediately proceed into to audience questions. So I encourage everyone to begin to propagate the chat box with questions as soon as they arise, and we will try to get to as many of them as possible. And so with that, I will turn the podium over to Gabby.
Thanks, Will, and thanks everyone for joining. And let's see, let's get the next slide up because we're going to jump right in. So we're talking about the results from the National Academies report on a research agenda towards atmospheric methane removal. I had the honor of chairing this report, and today we have with us two other members of the committee who will, Rob Jackson and Holly Buck, as well as Hannah, who contributed a paper, and we'll walk through that. So I just wanted to thank all the committee members who contributed this report. But jumping right in, we're talking about methane. Methane is not the same as CO2. They both have carbon, but they are different in really important ways that are key to understand when thinking about why one might even consider atmospheric methane removal. So we know that methane in the atmosphere is currently the second most important greenhouse gas contributing to human-driven warming, second only to CO2. And some of the ways that methane differs from carbon dioxide are that methane is much more potent at trapping heat in the atmosphere, and that then 90 plus percent of that gets trapped in the ocean. So there's that flywheel effect. And that is a methane is about 80 to 90 times more potent in that heat trapping effect over the first 2 decades of time. And most people are probably more familiar with the 100-year global warming potential equivalency, closer to about a 30 time more potent. And the global emissions, and just that timeline and that potency really has an effect on how methane interacts with the climate system. It really is a strong lever on rate of warming, whereas CO2 builds up the atmosphere and is really a determinant of the total peak warming magnitude. And the global emissions for methane sources, about 2/3 of methane emissions currently are associated directly or indirectly with human activities, which is bad news. But the good news is that because methane is so much shorter lived than carbon dioxide in the atmosphere, methane only sticks around in the atmosphere for about a decade compared to the thousands of years for CO2. It's this combination of potency and short lifetime that makes methane so important in terms of that lever on rate of warming and the potential to slow warming in the near term and contribute to essentially sooner limiting that peak as we go along with managing and mitigating CO2 as quickly as possible. Methane also is much more reactive in the atmosphere than CO2. And one of the cool features about this is that the more methane we emit, the longer it lasts in the atmosphere, but conversely, the less methane we emit, the shorter its lifetime in the atmosphere. And that has to do with some of the reactions that Hannah is going to get into in her part of the presentation. And finally, just to give you a sense of scale, if we were to eliminate all methane emissions, currently that's about a half a degree of warming Celsius that methane is contributing to global warming. And so this is a real significant potential lever, but that potential to eliminate methane requires a combination of reducing sources, but also reducing sources for which we have mitigation potential, but there are some sources for which we currently do not. And that's one of the motivations for why scientists are starting to consider atmospheric methane removal. The next slide, please. So let's get into some definitions to be really clear. So first, what do we mean by atmospheric methane? Atmospheric methane is methane in the free atmosphere. That's currently at a concentration of about 2 parts per million. So that's about 2 molecules of methane for every million molecules of air in the atmosphere. For folks who work in the carbon dioxide removal space, this is really important because lower concentration means much, much harder to target for removal compared. CO2 is hard to remove, methane, that much lower, that much harder, that much scarcer. And as you can see in this graphic where we've got 3 different panels and the kind of the leftist planet, top of the leftist panel, leftmost panel, we see the reaction that naturally takes place, that removal mechanism for methane, which is primarily through a reaction with the hydroxyl radical. There's a secondary, much smaller reaction, removal with chlorine, with reactive chlorine. As I was saying, about 2/3 of methane emissions come from anthropogenic sources. They're illustrated here. In the bottom, you see fossil fuels, agriculture, and waste. And then in the middle panel, thank you for that little, we have some of the examples of existing mitigation strategies for anthropogenic sources. And we want to make a distinction here by what we mean by methane mitigation, which is any human intervention that reduces methane emissions at the source. These are typically interventions that are on anthropogenic methane. And then on the right, a little sneak peek at the 5 different technology options. that Rob will get to shortly for atmospheric methane removal. But first, what do we mean by atmospheric methane removal? The definition in the report is any human intervention to accelerate the conversion of methane in the atmosphere to a less radiatively potent form, or to physically remove methane from the atmosphere and store it elsewhere. There's another piece of this, which is in the context of ecosystem. It is enhancing, reducing the flux to the atmosphere or enhancing the net flux into the ecosystem. Just to expand on that a little bit further. And so a really important conclusion that we make in the report is that atmospheric methane removal technologies, even if successfully developed, will not replace mitigation on timescales relevant to limiting peak warming this century, just to kind of bound the expectations on scale and time. And again, mitigation, I think the CDR space has this too. Don't put it in the atmosphere in the first place. If you can turn a wrench to stop the leak, do that first. All right, next slide is the committee was tasked in our report with considering scenarios for why one might want atmospheric methane removal. And so we considered 5, and 2 are illustrated here. And part of the reason, and this is in chapter 3 of the report, is that there are different needs. CDR is addressing a specific need, which relates to the fact that carbon dioxide builds up in the atmosphere. Again, methane is different. And so the kinds of motivations for methane are going to be different. So the first on the left here is illustrating this gap, this mitigation technology gap, which is that about 500 teragrams, about a billion tons of methane are 500 million tons, sorry, math, are emitted at below 1,000 parts per million concentration. And this is actually an important moment to do a quick distinction. A lot of people are familiar with capture of methane from concentrated sources, landfills, anaerobic digesters. That's all good if it's above 5%, right? We're talking about below, because that can burn. But there's a whole majority of methane emissions that are very diffuse, that can't be combusted in that way, for which other conversion and removal technologies are necessary. And for which, once it's in the air, we don't have capacity options in our toolkit right now. And so exploration of some of the technology approaches we're going to be talking about now would expand that toolkit. And then on the right, this is a concept I think is a bit analogous to why we have the concept of carbon dioxide removal, which is there is the potential for a gap in our methane emissions trajectory between where we want to be, that green line, for staying consistent with a particular climate goal, where we're going, that blue line, and how far down we can pull on that blue line of emissions using existing mitigation technologies. Then there's that dashed line on the top, which is the fact that natural methane emissions, we have evidence that those are increasing, in particular from the tropics, with potential also from Arctic permafrost areas. And together, all those pieces could mean that there's a difference between where we want to be in methane emissions and concentration and what we have the tools to get to. And that atmospheric methane removal technologies could help us fill that gap. Next slide. And with that, I'm going to hand it over to Rob to take us through those technology approaches.
Thanks, Gabrielle. Thanks everyone for being here. Part of our job on the committee was to define the set of atmospheric removal technologies that we would consider for this assessment. And we grouped them into 5 broad categories, some of which have direct analogs to carbon dioxide removal and some of which don't. And David, you may just step through the animation to get all 5 up there. It might be simpler. Thank you. So for instance, we have methane reactors, and these are analogous essentially to direct air capture units. You can imagine a bounded system, a reactor in which air is moved through that system, typically with fans blown through it. And an oxidizing agent is contained in that reactor, and it destroys the methane, converts it to carbon dioxide or some other form. So that's what we call methane reactors. So these are purpose-built, bounded systems. So you can move the air across a catalyst or an oxidizing agent, or you might have a methane concentrator shown on the left here. And there isn't a concentrator today for methane the way we have scrubbers or agents, chemical agents for carbon dioxide. There's nothing like a dryerite used in submarines to scrub carbon dioxide concentrations from air. We don't have those chemicals yet for methane. They would be extremely useful because any opportunity to increase the concentration of methane, as Gabrielle mentioned, would enhance the performance of all of the other technologies that we're evaluating. So that's why methane concentrators are on our list. They are not themselves methane destroying or removing technologies, but they would aid all of the other technologies we talk about. We also looked at ecosystem enhancements. We know that ecosystems both release methane in low oxygen environments and waterlogged environments, but microbes also they eat methane in drier situations for energy. So we know microbes work at 2 parts per million. They work at very slow rates. So if we were to enhance ecosystem uptake, this might include increasing the number of methane-consuming microbes in a particular system, starting likely with agricultural systems, if this were to happen at all. So you can increase the number or the abundance of microbes that eat methane. You might also think about ways to boost their physiology or their activity. That boosting could come from a chemical additive, perhaps a copper or an agent that changes pH or the redox position. You might also consider about changing the performance of these microbes through genetic engineering, and that would be more complicated to release those microbes into the environment. But in principle, at least, there are a lot of opportunities to enhance what microbes already do. We call that ecosystem enhancement. You can think about surface treatments here. Imagine a photocatalyst that reacts in sunlight that's on the surface of a roof, or perhaps on the surface of an airplane or a vehicle, a train or a car. Any system where air is moving across a surface could, in principle, take advantage of a methane oxidizing catalyst or material of some sort. So we call these surface treatments. And finally, just as you can move air through a reactor, you can also, for methane, release the oxidizing agent into the open air. And this is different than for carbon dioxide. There isn't really an analog for this directly. So the ways that methane is destroyed in the environment are chlorine and hydroxyl radicals, primarily nature's detergents. And we could enhance the production of those oxidizing agents and release them into the open air with a lot of caveats that we'll come to here in a second. So next slide, David, if you will. And I won't go through each of these boxes by any means for this technology assessment for the 5 technologies, but maybe I'll pull out one thing on each. Reactors, for instance, are the most feasible, the easiest to monitor. You have a airflow in and out. You can measure the concentrations of those gases. So MRV, monitoring, reporting, and verification would be relatively straightforward. But reactors have high energy costs and take a lot of air to remove a ton of gas. So they're likely to be more expensive than some of the other approaches, and they also need to perform at close to room temperature. It isn't feasible for us to heat air up to 300 or 400 degrees C, which is the current rate of many catalyst technologies. We need to have that very close to room temperature, or the heating costs simply become prohibitive. As I've mentioned, concentrators aren't themselves a methane removing technology, but there's something that could aid all of these other materials. If we had a soda lime analog that's for carbon dioxide, a soda lime analog for methane removal. So we call for research in concentrators. Surface treatments are likely to be photocatalysts, as I mentioned. There we need advancements in quantum efficiency. They need to be more effective per photon. of sunlight, and you have concerns about durability and fouling. How do you clean these surfaces, and how often do you have to reapply them, which affects the cost. For ecosystem enhancements, microbes do this already, but they do it at relatively low rates. So these ecosystem enhancement technologies would have to boost the numbers or the activity of microbes on plants or in the soil. And finally, for the last one, atmospheric oxidation enhancement, this open air approach, where you don't have to move the air energetically. It's almost certainly the cheapest potential methane removal technology per ton, but it's the most uncertain in terms of social acceptance and unintended consequences. We want to be very careful that we don't produce unexpected gases or undesirable gases in the atmosphere. Maybe next slide, please, David. So the committee believes that all methane removal technologies will impact the composition of the atmosphere in complex ways. None of these systems have lasers that just act on methane. We need to be careful about what else we're touching and changing. Um, the committee believes that closed systems, these reactors will be easier to monitor for the reasons that I've mentioned, where you're passing air into and out of, you have a bounded system, and you can measure the concentrations of all of the gases that you wish to. Open systems are more difficult to monitor. You have to follow a parcel of air and look at changes in chemical composition across that parcel of air, the kind of work that Hannah models. Um, AOE, this open air enhancement, it's the technology with the greatest potential consequences for methane removal, but also for other changes. The range of modeling scenarios that the committee commissioned for this report had methane increasing or decreasing depending on the amount and location and scale of these agents released into the air. And they also affected stratospheric ozone in some cases. So we need to be really, really thoughtful and careful about the chemistry and humble about these approaches before deploying any of them. And the committee does not recommend deployment at this stage. So let me stop and turn to Hannah.
Thank you, Rob, for that great introduction. Yeah, so as Rob has alluded to, I was commissioned for this report to write a study focusing on the intended and unintended impacts of enhancing the atmospheric oxidation of methane. So as we've heard, methane is primarily removed from the atmosphere by being oxidized by the hydroxyl radical or chlorine radical to form CO2. And so we don't know yet exactly how we could go about increasing the levels of hydroxyl radical and chlorine radicals in the atmosphere. Some ideas would be to emit hydrogen peroxide or H2O2, which I'm showing on the left, potentially from a tower or some other more diffuse source. And then that hydrogen peroxide could be photolyzed to form hydroxyl radical that reacts with methane. It also reacts with many other things in the atmosphere. For chlorine, one proposed idea is that particulate iron could catalyze the release of chlorine from sea spray, and then that gas would again photolyze to the radicals that react with chlorine. So depending on how exactly this happens and what methods are used, I'm summarizing the impacts on methane on the right. The OH-based methods, if you do increase OH enough, you will get a decrease in methane. For chlorine-based methods, it really depends on exactly how we go about trying to release chlorine. There's a lot of uncertainties in specifically using iron to catalyze chlorine, and depending on how you represent that process, you may or may not get enough of the chlorine radical specifically being increased to have a significant decrease of methane. And as I've mentioned, these radicals that react with methane also react with many other things in the atmosphere. And so I looked at a variety of different axes. And so you'll see there's kind of pros and cons and different trade-offs depending on these different methods, as well as sometimes there's variations depending on what region you look at. So specifically, there's other climate forcers besides methane that are impacted by changing this oxidation. In all cases, when we increase kind of overall the ability of the atmosphere to oxidize chemicals, we produce more aerosol particles through that chemistry. And largely those aerosols have a cooling effect, so that could be an additional benefit for climate. On the other hand, for greenhouse gases, These can also oxidize other greenhouse gases. I looked at halogenated greenhouse gases, for example. So for OH-based methods, these largely are decreased. For chlorine-based methods, because there are some specific greenhouse gases that form through chlorine chemistry, some compounds have an increase and some have a decrease. So there's more that needs to be kind of looked into to see what the overall balance is on that. And then one concern would also be potential for ozone depletion. So chlorine itself can deplete ozone. Whether or not this ultimately reaches the stratosphere is a big question if we increase chlorine at the surface. There's also other ozone-depleting substances that can be destroyed or generated through reactions with the hydroxyl radical and the chlorine radical. So overall, I found that ozone-depleting substances were decreased when you increase hydroxyl radical, but some of these were increased with chlorine-based methods. I was only able to run my simulations for 1 year, which might not be enough time to fully understand how the stratosphere is impacted. It can take a long time for air to mix up into the stratosphere. So I didn't see any significant impacts on stratospheric ozone over the course of deploying these technologies for 1 year. But that definitely is something to consider for longer term interventions. And then finally, the surface air quality. So aerosol particles are not only a climate forcer, but at the surface, especially for smaller particles, which I'm indicating as PM 2.5, they're less than 2.5 microns. This is something that's regulated for human health. At the surface, they can impact our lungs, our respiratory system. And so again, because we're increasing the ability of the atmosphere to oxidize a lot of different gases that can transform them into more particles, I found overall an increase in particulate matter at the surface for both of these types of methods. Ozone had a bit of a difference where for OH-based methods, there were some regions where we had an increase in ozone and some where there was a decrease. And this has to do with the background atmospheric chemistry that's going on. What other anthropogenic emissions are there happening in that region? For chlorine, though, since chlorine directly destroys ozone, we see an overall decrease. So the last figure I'll show here is just an example for specifically looking at a hydroxyl increase case where we emitted hydrogen peroxide. On the left, showing how the ozone patterns may change, and on the right, showing particulate matter at the surface. So again, with ozone, we see in more populated areas an increase if we increase OH there, and that has to do with the anthropogenic emissions of things like nitrogen oxides from vehicles. And then for PM 2.5, I've highlighted in the black boxes are where we exceed the annual mean standard for PM 2.5 if we release this amount of hydrogen peroxide in regions that previously were not in exceedance of the annual mean health standards. So again, we definitely need to consider where we're doing this, how much we're doing this, and what all of these trade-offs are when we think about atmospheric oxidation enhancement. So with that, I will hand it off to Holly Beck.
Thanks so much. So I was one of the social scientists on this committee, and one of the themes that goes throughout this report is the importance of early engagement and governance. And sometimes people see these words and they assume that they have a restrictive function, but that's not how we were thinking of this. We were really thinking of these as two things that can enable research, not only constrain it. And so just a couple of definitions, what we mean by these terms. Governance, we're thinking about policy, but a bit broader. I'll talk about policy in a second. And we reviewed analog technologies because there's not a lot written on governance for atmospheric methane removal. We also looked at public engagement with emerging technologies and other climate intervention approaches, finding that engagement is going to be really important for all of these approaches, but especially these open system technologies before consideration of deployment. Next slide, please. And so we also looked at policy a bit in this report, finding that there's a number of legal and regulatory frameworks that would impact atmospheric methane removal. a lot of considerations about monitoring, reporting, and verification. Right now, researchers lack tools or capabilities that are affordable, accurate, precise, robust for field scale application, and for verifying the impacts of these open system approaches. I saw there's a question in the chat about market-based mechanisms. We find that if atmospheric methane removal technologies were to enter offset markets, there would need to be more fundamental policy research and MRV requirements to ensure that they actually did what we want them to in terms of contributing to additive reductions in atmospheric methane concentrations. These are really early stage approaches. And we did look at cost, finding that technologies could plausibly be cost competitive with some mitigation approaches for methane emissions. However, methane emissions mitigation remains the most cost-effective means of addressing the growing concentrations of atmospheric methane. Next slide, please. So the committee recommended essentially a two-phase research agenda because, as I've said, and as you've seen, these are very early stage technologies. And so that makes it hard to even know what sort of investments to make in them. So for the first phase of this research agenda, we have 5 different research areas that we're recommending. Some of these are foundational research that seek to fill those really basic knowledge gaps in understanding. And importantly, that, investing in these for atmospheric methane removal can also advance other sorts of fields. And so that would be methane sinks and sources, atmospheric methane removal technologies, and fundamental social science research about some of these things, like how engagement can work. And then in parallel, we're recommending all of these 5 be pursued. Systems research, those areas look more at what would it take to develop and deploy these technologies at scale? What would the implications be? So that would be applied social dimensions research for atmospheric methane removal and understanding the applications of atmospheric methane removal. And I will turn it over to the next speaker.
Thanks, Ali. So just to dive a little bit more deeply into those 5 areas, and that these puzzle pieces are meant to show that these should be connected. And a key component of the recommendation is that the research, so it's a 2-phase recommendation, that the research be started with urgency so that in 3 to 5 years, a second phase assessment could come back and do a more robust assessment on the feasibility, the viability, the acceptability of each of these approaches. And so in blue, these are the puzzle pieces. Oh yeah, and the third part of that is, as Holly was alluding to, the real criticality of early integration of the social science aspects, especially any kind of emerging technology. Any assessment is really fundamentally a socio-technical problem. So we have to understand some of these market questions that are being asked at a more fundamental level, in terms of, are the markets doing what they're supposed to do? How would adding any type of atmospheric methane removal technology into those markets affect those markets? And how publics form perceptions of these kinds of emerging climate intervention technologies. But research area 1, so that just to go back to the order of these things, is foundational research on those methane sinks and sources, really better understanding, in particular, of the sinks. There's been a lot of attention on sources, but less attention to the atmospheric chemistry and the oxidative capacity and controls on that oxidative capacity, and the role of ecosystems, not just when there are bursts of methane out, but when those methanotrophs that like to eat methane, when are they happy, and what kinds of management practices could enhance that, or amendments to those soils. And similarly, research area 2 is, and so just to what Holly was saying, these kind of foundational areas, there are a lot of people who might not consider themselves researchers, atmospheric methane removal researchers, but there are a lot of people doing work on the methane cycle, for example, that's relevant to better understanding these systems, and in particular, what we can measure and what we would need to be able to measure small differences over large areas, for example, for some of those ecosystem uptake enhancement approaches. The second area is foundational research on the technical technologies themselves. This is everything from materials science around the catalysts that would be used in the reactor approaches and the surface treatments, to some of the fundamental understanding of microbiology. We actually don't understand that well the wild methanotrophs, all of the ecosystem controls on their ability, because they do eat methane at this very low concentration. So what enables that, what prohibits that, how they interact with their surroundings. And then in the foundational social science research areas, this is really getting to this importance of asking the fundamental questions of how, when, in what stage of technology development, and in what form does public engagement enable that research. I think it's really important to think about and have a better understanding of those questions. That is critical to establishing an understanding and legitimacy, for example, to have those conversations. But the more generally, just better answering what are the forms of public engagement and how those inform and interact with the kind of work on these emerging technologies. And then in orange, we have what we call the systems level research areas, which are very specific to the technologies of atmospheric methane removal, and touch on the social governance related questions that would affect potential applications of atmospheric methane removal technologies. And in terms of like, what kind of considerations you have to take into place in terms of the communities where one might cite some of these technologies. In research area 5, I think folks in the CDR community would be very familiar. This gets into some of the kind of systems, the energy system interactions, the material needs that one would need, and how that works with other interventions in the space. For example, the hydrogen economy. So going back to what Hannah was showing, hydrogen competes for the hydroxyl radical. And so, for example, if one has a leaky hydrogen system, that actually could extend the lifetime of methane in the atmosphere. So these types of interactions that one needs to understand. And so going to the next slide. This is kind of a top level summary of how the committee rolled up. So for each of these research areas, if you look in the report, there are a number of more specific questions. And when we assessed in terms of buckets of low, medium, high in dollar amounts, and low, medium, high in terms of priority information, so that a second phase assessment can get this more robust assessment. So when you'll see that prioritization is in that context, and we roll up these numbers, what we find is that on the order of $50 to $80 million per year over 3 to 5 years is our rough estimate of what it would take to answer these foundational and system questions in a timely manner to be able to do this more robust assessment. And it's really important that when developing research programs, when we're developing projects, that the research and considerations be conducted in a responsible manner. All right, let's get to some concluding thoughts. So yes, so just to get back to this idea of responsible research, what we mean by that, this needs to be a transparent and interactive process through which society and researchers are mutually responsive to each other. And this is one of the reasons why I think it's important, and the report highlights in that far box on the right, there are a lot of public agencies to get involved, but there's also opportunity for private sources of funding. And there are also kinds of codes of conduct types of approaches that have been adopted. I think the CDR community is very aware of this. The Institute is very focused on this. It's really important when you have an emerging technology to take seriously what kinds of public concerns there may be, and be involved in capacity building and early identification of those concerns, which can also drive some of the research questions and essentially have that very positive interaction. And so I think with that, I think my part is over. Some concluding thoughts, and then we'll get to David. Sorry, keep dangling that. So some concluding thoughts here is that, again, mitigation, got to do the mitigation first. Atmospheric methane removal, interesting but hard, not a silver bullet, but potentially can help expand our mitigation portfolio and help address this potential methane emissions gap that is in the context of the urgency of slowing warming. That this is, again, we didn't show the TRL levels, but in the context of the atmospheric, that 2 ppm level, all of these 5 technologies we're talked about are TRL 1 or 2 level. So this is still very early stage for that very low concentration atmospheric methane removal. And again, this is our vision for these foundational priority and systems research that should commence with urgency in the next year if we're going to be able to get answers and get projects funded and research done to be able to have this second phase assessment within 3 to 5 years. With that, David, over to you.
Thanks, Gabby, and thanks to the rest of the presenters. Really briefly, Spark Climate Solutions, we're a nonprofit focused on field building, and one of our areas of focus has been methane removal over the last few years. And I just want to talk in parallel to the National Academies process. We were working collaboratively with other with researchers in the field and other organizations to move that foundational research forward, because indeed we really are very early in exploration around methane removal as a concept, or methane oxidation as a concept. And just rather than going through this in any detail, I want to get to questions. One quick thing, we ran a couple of rounds of exploratory grant proposal requests last year, received well over 100 high quality submissions. We selected 12 grantees from that. We've done some grants as well on directed projects over the last 3 years as well. And one thing to highlight is, in addition to it all being quite early, and I'd love to see Hannah's analysis. I think there's a lot of work to do on the modeling side to build off that, both the high resolution, box scale, local scale, and also Earth scale, given how new the integration of halogen chemistry and these sort of cloud aerosol interactions are in a lot of these models, since the focus has initially been on carbon dioxide alone. I think the thing that's really interesting, one thing that's coming up in some of the interesting proposals that we have seen, has been that there have been really interesting potential co-benefits with some approaches to carbon dioxide removal. As Rob laid out in reactors, these reactors could be potentially co-located with direct air capture approaches, adding to the climate benefit of that direct air capture by oxidizing methane and potentially other greenhouse gases at the input. And slightly increasing the amount of CO2 that would then be potential for capture by a couple of ppm. And then also enhanced rock weathering is another area where some of the scientists that some of the early funding we provided has been studying in what scenarios might that enhanced rock weathering approaches with particular amendments could also decrease methane flux to the atmosphere. And yeah, anyway, there's so many more questions and answers here, and there's a lot to be explored. One other thing that did come up in the questions, and I wanted to address it briefly, which is one of the technological approaches to sort of developing reactor technologies would be to start at these higher, at basically the point source of emission, which I would say is probably most closely analogous to carbon capture and sequestration, or carbon or CCUS, where again you're just oxidizing the methane rather than necessarily doing anything with it, depending on that concentration. But it's another interesting analogy. I don't want to take more time because I want to make sure there's time for questions. Yeah, thanks for listening.
All right. Thank you very much to everyone for that excellent overview. And given our time constraints, I'm going to start with some of the audience questions, and then if there's any remaining time, I'll ask a couple of the questions that I had. One question, it's disappeared from the box, but I think it's still a pertinent one. And it's one that, of course, those of us that are in the carbon removal community struggle with all the time is is how we finance this, right? Assuming, for the sake of argument, we're able to traverse all of the imposing scientific research questions and legal questions and questions of equity. Uh, uh, at the end of the day, um, do you contemplate that large scaling of methane removal, which I realize is not quite as imposing in scale as carbon removal, but nonetheless imposing, that large scale methane removal would be effectuated through tapping into voluntary carbon markets or compliance markets, or might this be potentially a pay for practice sort of model? Anybody want to take that on?
I'm interested to hear other people's views as well. I think it's very early. It's kind of too early to tell, and I think it depends. It'll depend on approach, or could very well depend on approach, uh, depending on what proves out, right? If anything proves out. So in an ERW type, co-benefit, then it could really follow the model of being something that's additive to pay for practice. If that's actually what proves out in ERW, I think it's even too early to say that that's necessarily going to be the model there. I think with reactor-based approaches, when you're talking about methane emissions destruction, where you're destroying, you're basically oxidizing the methane, the low concentration methane before it gets into the free atmosphere, you could see that as just another mitigation approach, right? And so it could be compensated similarly to other mitigation. When you're talking about something like atmospheric oxidation enhancement, I mean, this is an open system intervention. It's somewhat similar, that has some similarities to marine CDR, but then also some differences. And there's much more complexity and more to explore, as Hannah laid out, and Holly as well. And uh, in terms of use and purpose, it could have much more to do with, the risk of rising natural emissions as opposed to addressing any anthropogenic emissions. In which case, that feels like a public good and something else. But again, that's a thing that simply I don't think we know, particularly given that we're at such an early foundational stage of the research itself. Rob, Gabby, Hannah, anybody, or Holly, any other perspectives here?
I could go just very briefly and we'll get to the other questions. I mean, there's the potential for voluntary markets for methane, just as there are as there is for carbon dioxide removal. But just as for carbon dioxide removal, voluntary markets alone will never get us to scale. You'll never get to the billion-ton scale with CDR, contracting with Stripe and Microsofts of the world. Same is true for methane. So we would need either a regulatory mandate or some sort of public price on emissions for methane. I think the same is true for carbon dioxide. Last thought, there are large methane emitters, particularly dairies, who want to zero out or offset their emissions with methane action, not by swapping it or converting it or with some sort of fungible way to carbon dioxide. So there are companies, I think, who will engage in the methane space that may not engage in the carbon dioxide removal space. But I'll stop there.
Okay.
Yeah,
Any other?
and Holly spoke to this in her comments of the report. The report does talk about this kind of markets question, but as David was saying, this is still very, very early, and even the question itself is worthy of research. How might in methane removal fit in these markets, and how effective, how are the markets already operating today versus how we think they want them to operate? So we actually take that in the report a step higher in terms of the kind of research that is needed.
Okay. All right. Another question. Given the early stage that methane removal technology is as a whole, what short-term 10 to 20-year targets do we need to hit for it to make sense to scale this technology, as opposed to putting resources, financial and science, to accelerating the CO2 removal technology, which is growing, right? It's the dilemma that we face in the context of CDR also, right? Given a limited pot of resources, right? What is the optimal allocation of those resources, right? And I know it's an impossible question in many ways, but interested in anybody's thought about this.
So I think, I know, Rob, I think you also have thoughts on this, but I just, a key point here is the need to think about the problem that you're trying to solve and the difference between methane and CO2 that I started with. Methane is more potent, it is shorter lived, it is going to give you a much bigger bang for your buck on the rate of warming. And so this gets to that kind of those kinds of cases and this methane emissions gap concept and the fact that we have natural methane emissions that are increasing. So there are certain things in the mental model with which CO2 and CDR are being solved for are an assumption of the total amount of cumulative CO2 that can be added to the atmosphere to stay below a certain temperature. That doesn't give you as much of a lever on issues related to, for example, rate of warming or some of these natural emissions from methane that aren't even included in the calculation of the remaining carbon budget. Those are excluded because they are excluded from the models that were used to generate that. And so methane removal, atmospheric methane removal could be solving for a different set of issues and is that way not entirely fungible with carbon dioxide removal. And so that would just be one additional consideration. And further, the way that you would try to have the same temperature impact, there's a fundamental difference here between emissions and temperature impact that have to do with those fundamental differences between how methane and CO2 act on the atmosphere. So just a few consideration points there.
I would add one thing, which is that the foundational research around the atmospheric chemistry and the biosphere biology associated with methane and other sort of more reactive greenhouse gases and the cloud aerosol interactions are things that are affecting both the rate of warming and near-term warming. And so, in the sense of relatively small amount of dollars towards better understanding those dynamics, almost independent as to whether or not any atmospheric methane removal technology actually proves out, could be basically have outsized value to risk management for the planet over the next couple of decades. And the work that Hannah and some of the other groups are now doing, incorporating these approaches in part because of this increased focus on this question, is actually improving our ability to understand sort of the near-term dynamics and climate impacts. So there's sort of a again, it's similar to Gabby in the sense that it's this the yes and it's also at a scale that is fortunately relatively small.
I just want to add one thing really quickly that I didn't directly mention previously, which is that methane is a precursor to ozone air pollution. So there's also that additional co-benefit for reducing methane and reducing ozone air pollution. And ozone's also another greenhouse gas. So that kind of additional warming effect is captured with methane as well.
Yeah. All right. Thanks for that. I have a question for Holly on the social science side of all of this. So the study indicates that public engagement would be an important component of AMR research, including at both the stages of potential deployment, well down the road, but also in terms of ongoing small scale research. But given the fact that our understanding of so many facets of AMR science are so rudimentary, what does early stage public engagement look like in terms of small scale research? Could you just map out kind of the broad contours of it, Holly?
Yeah, and so I'll be stepping out of this committee role and just giving you my expert opinion, independent of the work we did on this committee project. I think that it's always going to be very tailored to the context and the technology. So we're talking about five different broad categories of approaches here. I think that for some of these things, the engagement looks more like it would around direct air capture, and you have a number of companies, trying to figure out models for that, usually with some element of having meetings with key people in the community, maybe an open house early in the process, before construction. With other of these, where it's more even in the, research phase, um, especially with these open approaches, there may be models that researchers are innovating with ocean alkalinity enhancement, for example, that would be applicable anytime you have like a site where you're going to do a test of something and be monitoring it. I think there's a lot of opportunities that in general we're not taking in terms of community-based monitoring or including members of the community in the science itself that could be a fruitful area. Um, I could talk about this for a long time, but I'll leave it there.
All right. Thanks for that. Yeah, I think that last point is extremely important, or 2 points, right? Both the role of communities and participating in some of these things, which I think has been undervalued in terms of CDR also, and efforts to integrate research in a way across spectrums, including other mitigation approaches, including CDR, right, in ways that we're not thinking about, right? It adds another level of complication to all of this, but is probably really critical, again, given limited resources. So hopefully some of it occurs. So I've got one final question. So the NASEM report says that Yoon advanced this idea of atmospheric methane removal in 2009, and 15 years later, um, we look at this concept and it still remains pretty nascent, while many of the CDR options have seemingly advanced much more quickly. What factors would you attribute the different trajectories of CDR and AMR to date, and what does it tell us needs to be done in the context of AMR research moving forward? Who's going to grab that? Gabby? Go ahead. You.
Go ahead, Rob.
Well, I thought Gabby was speaking. Okay, sorry. Great question. Well, I think part of the answer is that there has simply been so much less attention on methane in general. I mean, we have to remember that the first global methane agreement was only signed a couple of years ago, the Global Methane Pledge. So there isn't nearly as much, hasn't been nearly as much done or policy attention or economic focus placed on methane. And as we've realized that these temperature thresholds like 1.5 are fast approaching, if not past, we're looking around for things that we can do more quickly in addition to the critical role of reducing carbon dioxide concentrations. And methane's the only greenhouse gas that allows us to shave peak temperatures over the next decade or two through mitigation or removal. So I think it's partly a lack of focus and attention. And fortunately, in the last few years, that attention is growing quickly. It's not the only reason, but that's one. And I'll turn it to Gabby or someone else.
Anything to add, Gabby, or anyone else?
Well, I see David wanting to jump in, so go ahead, David.
Oh, okay. Yeah, we'd also add that methane concentrations, right, had slowed, like their growth had slowed in the late 2000s, and have now sort of accelerating an accelerating pace, with some still remaining disagreement about the source of that acceleration. And historically, and still to this day, I mean, methane mitigation is the most powerful lever for reducing methane concentrations. It ought to be, because methane doesn't last in the atmosphere that long. And so the concept of methane removal felt like, well, we just need to stop the emissions. And as those concentrations continue to grow and our understanding of the natural system and the rising risk of natural emissions increasing over time, which are still not in the IPCC models, hopefully that will change, but currently it's still held flat. So that the sort of underlying risk of this baseline of methane in the background just increasing in spite of the fact that it doesn't last that long, just there wasn't a lot of awareness of this even in the last few years. This has been really, really recent. I think the NASEM study has been one way in which that's actually elevated even the awareness that there's any reason to contemplate this. And I think finally, the as climate impacts grow, looking for additional levers that can add to the ability of humanity to manage nearer term, rate of warmth, rate of warming and temperature is just it's like seeking additional tools. Whereas CDR, started getting included in the IPCC more officially, kind of in 2013, and it was a good thing, and it is a good thing, and it's going to be an absolute and is an absolutely necessary lever as well. And I think that's at least how I see it. And I don't know, Gabby, if you have anything to add.
I think just to put a fine point on it, if you care about rate of warming, which given that we just had a historic experience of 2024, we don't see that. I think that it's a little bit of an alarm bell for me personally. Just in terms of equivalence, there's a one paper cited in our report, and I know getting to the tonnage of CDR removal at speed and scale is already a challenge. Just imagine also trying to compensate for the temperature warming impact of those natural methane emissions. 1 ton of methane removal would, for the same rate of warming impact, require 125.5 tons of CO2, just based on one study. So you are looking at potentially a challenging CDR to meet our temperature goals multiplied by a very large factor that could be infeasible if we only have CO2 removal in our toolbox.
All right. Well, we have reached the top of the clock, and I thought that was very helpful. And I'd like to thank all of you for a great presentation, a great overview of yet another issue that we need to confront in the context of responding to climate change. But I think it's an important one. So I thank you all for your time. I thank our audience for their thoughtful questions. We'll be back next month with a couple more webinars, and so stay tuned. And until then, goodbye, everyone.